Let's wait for 1 more minute. All right, shall we get started? Okay, great. Well, believe it or not, we're at lecture 8, and we're going to go deep into the guts of pipelining today. Talk about data and control dependence handling, which we started last time. This is where we are in the grand scheme of a few weeks. We'll talk about issues in pipelining, but I'll jog your memory first. But before that, these are some readings for the next few lectures. This paper actually covers a lot of things on advanced pipelining, interrupt and exception handling, out-of-order and superscale execution that we will cover in the next few weeks. How many of you have started reading that one? No one? Okay, you guys should. These are required readings, by the way. This is the supplemental reading. I guess you could read that. This paper talks about branch prediction, which we will cover next in the next lecture. That's a very nice paper, actually, that talks about how to design branch predictors. This is a paper that we will talk about briefly, and it's a modern implementation of an out-of-order execution processor. Well, modern, 1999. It's actually a processor that was designed in 1995. And this paper talks about precise interrupts in pipeline processors, and we will cover this when we talk about state maintenance and recovery. This is just to give you a lay of the land of what's coming next. But definitely read this paper, Smith and Soy. That's a good overview of what we will, basically everything that comes after. Okay, let's recap the last lecture. Hopefully you guys remember. We wrapped up microprogramming. We talked about horizontal versus vertical microcode. We talked about nanocode and millicode. So hopefully you know these. We went through these relatively quickly, but these are relatively easy concepts. We started pipelining to overcome the disadvantages of multi-cycle machines. We talked about the basic idea. I gave you the laundry analogy, right? Nobody does laundry like a multi-cycle machine today. Everybody pipelines their loads, right? So it makes sense to do pipelining. We talked about the characteristics of an ideal pipeline and how those characteristics are really violated by instruction processing. We talked about the data path and control. We talked about some issues I will briefly talk about again. We talked about resource contention, dependencies and their types, which we will focus on today, control versus data. And we talked about 3 types of data dependencies: flow dependencies, anti-dependencies, and output dependencies. Talked about 5 fundamental ways of handling data dependencies. Talked about data dependence detection at the very end of the lecture. Remember interlocking? I'll start with that again over here. Somehow somebody needs to detect this dependence. And we talked about doing it in hardware. We talked about scoreboarding versus combinational logic to actually do this dependence detection. These are actually commonly implemented in today's processors, both scoreboarding and combinational logic. But if you just take one bit and do nothing else, remember scoreboarding had a valid bit associated with a register file, right? Each register, right? If someone is actually writing to the register later in the pipeline, that valid bit is not set. That's a very simple approach, but it has its limitations. Like we talked about the write after write and write after read dependencies that are not handled well with scoreboarding. Basically, you need to stall on those dependencies. Of course, you can enhance scoreboarding by adding more combinational logic, as we've discussed, to actually handle those dependencies, such that you don't need to stall on those dependencies, at least in a pipeline. So we will cover more of this stuff today. Look into data dependence detection, and look into the design of a pipeline, which you will implement in your later labs. So some issues in pipeline design, I go through this really quickly because we've covered all of this, but balancing work in pipeline stage was important, you remember? We'll talk a lot about how to keep pipeline correct, moving, and full, which is data dependence handling, resource contention handling, and handling of long latency operations. Exceptions and interrupts we'll cover later. And today we will focus a lot on minimizing stalls, actually. A lot of data dependence and control dependence handling is about reducing stalls, because these dependencies cause stalls in the pipeline. Okay, what are dependencies? We've talked about this. So they dictate ordering requirements between instructions. And you need to somehow detect this dependence so that the pipeline is correct, right? And that's the idea of interlocking. And we talked about software ways of doing it. We'll talk about that more. If the hardware doesn't have any ways of detecting the dependence, somehow software needs to handle it. And the MIPS design was initially done to actually put the burden all on software, such that the hardware doesn't need to do any interlocking, such that the hardware is kept simple. Right? But then we talked about hardware-based interlocking mechanisms. We'll assume hardware-based interlocking, but we'll talk about software-based interlocking a lot also later in this lecture. I'll give you examples actually. So okay, now we know how to detect dependence in hardware, right? Either using a scoreboard or using combinational logic. What do you do afterwards? Basically, dependence between two instructions is detected before the communicated data value becomes available. We talked about this also. One option is to stall the dependent instruction right away at the instruction decode stage, right? You can detect that dependence and you can stall that instruction right away. Or you can forward or stall the dependent instruction only when necessary. This is the idea of data forwarding and bypassing. And there may be other options, which we briefly discussed last time. Actually, more than briefly discussed, probably. For example, you remember value prediction, right? Predict the values and not stall. We'll get back to that too. So this is where we stopped last time, data forwarding, bypassing. I'll pick up with this and then we'll go into the implementation of stalling and data forwarding in a real pipeline that you will actually design also. So the problem is, if you stall when you detect the data dependence, maybe you're being conservative, right? Because a consumer instruction now has to wait in the decode stage until the producer instruction writes its value into the register file. But the value that is produced by the producer may already be available, right? For example, if the producer, if the parent, if you will, is an add instruction, it produces its value at the end of the execution stage. After the ALU computes whatever it's computing on the source operands, the value is available. Why wait until the end of the write-back stage to actually communicate this value to the dependent instruction? So our goal is to not stall the pipeline unnecessarily. And the observation is that the data value needed by the consumer can be supplied directly from a later stage in the pipeline instead of only from the register file. Basically, the idea of data forwarding is to add additional dependence check logic and data forwarding paths, buses, or interconnect, to supply the producer's value to the consumer right after the value is available. And we'll go into this in more detail. Basically, that's not laptop 2. Document camera. Okay, good. So if you look at this pipeline over here, instead of the instruction in the decode stage waiting until until its parent instruction or producer instruction writes its result in the write-back stage, you can provide a forwarding path from the ALU such that this instruction that's waiting over here can get the results right away after the instruction that's producing the value produces that value. That's the idea. And you can provide forwarding paths from here as well and from here as well. And we will see those forwarding paths. And the benefit is now consumer can move in the pipeline until the point the value can be supplied. Right? You don't need to wait at the decode stage. Or maybe you don't. Maybe you move on before the decode stage. It really depends on the structure of the pipeline. In this case, you may need to wait in the decode stage. Okay, we'll see this in more detail. This lecture will be about a lot about implementing bypassing, actually forwarding. But before I go into detail, I'll just point out that control dependence is a special case of data dependence. It's really data dependence on the program counter, right? If you view program counter as a register that contains some data value that's used as an address of an instruction, it's really data dependence. So, but it's a little bit different because it's really asking the question, what should the fetch PC be in the next cycle, right? It's happening over here. When you fetch an instruction, in the next cycle you need to fetch some other instruction. The question is, what do you fetch? Well, you need to know the address of the next instruction. Yes?
All right, just one thing we are wondering is, you mentioned the forward path, right?
Uh-huh.
On the diagram, I think you meant by the write back path, not the forward path.
What path?
Because you were saying there's a forwarding path from write back to a decode, but I think you meant implemented as a write back instead of the forwarding path.
Oh, initially.
Yeah,
In this
forwarding
pipeline.
path will be going to the execution unit.
You mean when I describe this pipeline?
Yes.
So this pipeline has a write back path, right?
Yes, but I think you.
Okay, when I first talked about it, I said write back. Okay, that shouldn't be forwarding.
Yeah.
Was that unclear? Okay, we'll get back to it. Okay, where was I? So the fetch PC, when you fetch an instruction, you need to know the address of the next instruction, right? To basically move the pipeline. And all instructions are control dependent on the previous ones because all instructions implicitly specify a next instruction, right? In a von Neumann model, at least. So if but this becomes more interesting if the fetched instruction is a control flow instruction, is a non-control flow instruction, is a control flow instruction. So if you have a non-control flow instruction, the next fetch PC is the address of the next sequential instruction, right? That's simple. And hopefully you can compute it easily because it's PC plus the instruction size. Assuming your instruction size is fixed, you kind of know your next PC. If it's not fixed, then you have a problem. You need to decode the instruction to figure out the next PC. This is easy to determine if you know the size of the fetched instruction, as I said. The problem is if the instruction that is fetched is a control flow instruction, now the question is how do you determine the next PC? Right? You have a branch instruction that you're fetching, and you want to determine the next PC. In fact, you don't even know if you're fetching a branch instruction, right? How do you even know whether or not the fetched instruction is a control flow instruction? Because you haven't even accessed the, if we go back to this figure over here, we haven't even accessed the instruction memory yet. We haven't even decoded because the next stage is decode. But by the time this instruction moves to the decode stage, we need to be able to generate a next fetch address into the program counter. So that's the problem with the control dependence. It happens at the very beginning of the pipeline. So it's a special case of data dependence, but it affects the entire pipeline, whereas data dependence can be handled in the rest of the pipeline. That's why it's an important special case of data dependence, because if you actually don't know what instruction you're fetching next, your pipeline can become empty until you figure that out, right? Okay, any questions? Shall I move on? Okay. Okay, let's go into more depth and into the implementation of data dependence handling. Remember, these were the data dependence types. Flow dependence is the fundamental dependence. It's the read after write dependence. This instruction reading register 3 that this instruction is writing. Anti-dependence and output dependence, these are actually false. They're also called false dependencies. They're false because this instruction really doesn't need R1, right? It's really writing to R1. It's really a dependence on the name rather than the value. There's no communication that's happening between these two instructions. Same is true for this output dependence over here. So remember, I said that this happens because you don't have enough registers in the ISA. If you had enough registers, you would not do that. Right? There's no reason why you would assign R1 to this instruction's output, because there's no relationship between the value stored in this R1 versus in this version of R1. You're really redefining what's in R1. You're really generating a new value and overriding what's in R1 over here. So these are false dependencies, but they can still cause problems. Because they're actually false dependencies, they're relatively easy to handle, and we've talked about how to handle them, right? You can write to the destination register in one stage. I keep doing the wrong thing here. And in program order. Okay. I guess I can go back. All right, why not? Is this too confusing for you guys? Okay. So basically, as long as you ensure that you write to the destination register only in this stage and in program order, well, hopefully you'll write into program order if you're writing in this stage, then write after write and write after read dependencies will not cause a problem as long as you handle the dependency check correctly, as we've discussed last time with scoreboarding or with hardwired logic. But flow dependencies are more interesting because they do cause stalls. You cannot fix them just by doing that. And we've talked about 5 fundamental ways. I'm going to briefly flash this and go into how to handle this, how to implement some of these. You can detect and wait. We'll see how to do that. You can detect them forward, as we've discussed. You can detect and eliminate the dependence at the software level. And this is the software-based interlocking. We already talked about this. You can predict the needed value and execute speculatively and verify. You remember the discussion last time? That's actually an interesting way. Or you can do something else, fine-grained multi-threading. And we'll talk about this in more detail in control dependence also. This is a fundamental way of eliminating any kind of dependence. I guess before I move on, I'll give you an announcement of a seminar because it's really relevant to what we've discussed last time. We have a visiting student, Arthur Perray, from INRIA, France, who will talk about practical data value speculation for future high-end processors. Basically, this is value prediction. And he's doing his thesis on the topic. And he's giving a seminar on Thursday. So if you have time, I would definitely encourage you to attend to see the effect of value prediction on modern processors. So if you look at the summary over here, he says value prediction was proposed to enhance the performance of superscalar processors by breaking read after write dependencies. We've already learned about that. The processor actually doesn't need to be superscalar. It can be pipelined also. But this has a bigger effect if it's superscalar. Remember, superscalar is a processor that can fetch, execute, and retire, finish multiple instructions per cycle. However, it has generally been considered too complex to implement. We've actually talked about how to implement this briefly, right? Last value prediction. Basically, remember the value that was produced by this instruction last time it was executed, and use that value as a prediction the next time it is executed. And this presentation will review different sources of additional complexity of value prediction and propose solutions to address them. So Arthur has been doing very interesting work in value prediction. So if you're interested in getting into the guts of it, I definitely recommend attending this talk. This kind of shows you that this is actually a topic that people are really working on. We're not talking about random stuff that no one cares about. But that's why you're here, right? You're interested in actually impacting the world. Okay, so let's take a look at, before going into value prediction, let's take a look at how we actually simply first detect these dependencies and handle them. This is a 5-stage pipeline that we've discussed, and assume that these are the instructions that you have. They may not make sense, but, well, actually they do kind of make sense here. This is the instruction that's producing register A, and this is the instruction that's consuming register A. If this instruction is in the decode stage over here, you need to wait until this instruction writes back into the register so that you can advance this instruction. So this instruction definitely caused a conflict. You need to somehow detect this dependence, right? Similarly, these instructions also need to wait until this instruction writes its result back into the register file, right? Only this instruction can advance, right? If you look at this, if you have 3 instructions, if you have fetched 3 instructions, only the 4th instruction can actually get the correct value, because by the time this instruction is fetched, this instruction at the top has already produced its value. So somehow we need to ensure that the distance between the producing instruction and the consuming instruction is, I guess, 4 in this case, right? Assuming you number the instructions 1, 2, 3, 4, 5, so that the pipeline can move correctly. So you can actually do this analysis more formally. I'll go through these relatively quickly, but for a given pipeline, you can ask the question, when is there a potential conflict between 2 data-dependent instructions? You need to consider the data dependence type, read after write, write after read, write after write. You need to consider the instruction types involved. And you need to consider the distance between the 2 instructions. So in this case, if you look over here, well, maybe I should do this so that everyone can see it. These are different instruction types in MIPS, and these are different pipeline stages. And I've listed over here when the instruction needs to read its source operands, if it needs to, and when the instruction writes its source operands, if it writes to a destination. And if you look at this, these instructions write to register. For example, the jump instruction, it is not data dependent on any other instruction, right? Because it's not reading a register. But everything else can be data dependent on a previous instruction if a previous instruction is writing to the same register. So we can actually, we'll take a look at the analysis of the pipeline. You can actually formalize this and do analysis. A lot of compilers actually do this kind of formal analysis. When is it safe or unsafe to move the pipeline, move an instruction that's in the decode stage of the pipeline? Let's look at the read after write dependence, because that's the more interesting one. let's assume we're doing register write at stage Y, and register read happens at stage X. And this is the ith instruction that's writing to the register, and this is the jth instruction that's reading. If you want to move the pipeline in a safe manner, this needs to be true. Basically, the distance between these instructions should be greater than equal to the distance between these stages when this instruction writes to the register file and when this instruction reads from the register file. Make sense? I mean, this is simple. This is kind of formalizing what we've said before, actually. But it's good to think about things this way also, because actually a lot of compiler analyses work this way. If they're closer, and if you don't have some dependence check logic, then you'll have a problem in the pipeline. You can do a similar analysis with write after read dependence and write after write dependence. So if this happens, for example, if your pipeline is designed such that this happens, then you have a problem, right? If this instruction can read from the register, and if that instruction writes to the register earlier. But remember that we can eliminate these dependencies by ensuring all instructions write to the destination register in program order and at the end of the pipeline. So that way this kind of violation doesn't happen for write after read and write after write dependencies. So we'll focus on the first one. So when does the first one happen? Basically, instructions IA and IB, where IA comes before IB, have a read after write dependence if and only if, you can basically read this, IB reads a register written by IA. But they need to be of these types. So instruction types actually need to actually be reading the register, and these are the instructions that write to registers. And if the distance between IA and IB is less than or equal to the distance between the instruction decode and write back stages, which is 3. Right. So you need to detect this dependence. And you can think about this. What about write after write, write after read? What about memory data dependence? So we'll ignore memory data dependencies in a lot of these cases. But again, if you assume that you're writing to memory in program order, at the very end, you won't run into issues. But you may need to detect the memory data dependencies if your pipeline is much longer, right? With this pipeline, we will not have an issue with the memory data dependencies. Okay, so how do we actually resolve this data dependence? I keep forgetting this, sorry about that. So if you're looking over here and I'm pointing here, I guess it's not going to work. And somebody needs to get me a big thing that has an effect on the screen. Kevin, you can do that maybe. Or you can figure out what we can buy. Okay, so if you look here, let's assume that instruction I is this one, and instruction J is this one. Instruction J is dependent on instruction I. And in program order, their distance is 1 over here. But if you look at the distance between write back stage and instruction decode stage, it's really 3. Which means that to be able to ensure that the pipeline operates correctly, we need to ensure the distance is at least 4, right? So how do you do that? Well, this way. We insert bubbles into the pipeline. Does that make sense? Basically, instead of moving instruction J, you wait until instruction I writes back its results, and only after then you can move instruction J. So I inserted 3 bubbles here. This is called a pipeline stall or pipeline bubble. But this bubble, if you will, can be implemented in software and hardware. Think broadly. This hardware can insert these bubbles by just stalling the instruction J over here, or the software can put independent stuff for the bubble such that the distance is 4. Right? Software can basically find independent instructions and stuff these bubbles with independent instructions, right? Then it'll still work correctly. And if the software doesn't find anything, it can put no ops in there, and the pipeline will still work correctly. Okay? Even if you don't have dependence detection logic. Okay. Basically, the idea of a stall is very simple, actually. Make the dependent instruction wait until its source data value is available. And how do you actually implement this in a pipeline? Let's assume that we're doing this in hardware now. You need to stop all of the upstream stages Upstream stages are stages. Now we can switch here. Basically, the instruction that's dependent needs to wait until the value is produced by the source instruction. You need to stop all of the upstream stages and you need to drain all of the downstream stages, such that the instructions over here finish. So how do you implement this? Well, implementation is relatively simple, actually. Basically, how do you stall the upstream stages? You have an instruction here that has, you have the instruction register here, you're decoding. You need to ensure that no other instruction overwrites this register, right? Otherwise you have a problem. So you need to disable latching of the PC and this register, this pipeline register. That's what this says, disable PC and IR latching. This ensures that the stalled instruction stays here and all of the previous stages actually stays here. Basically, more generally, if you have many, many stages before this, you need to ensure that those stages don't move. Basically, disable all of those registers, right? And how do you ensure that everything else moves? Well, this instruction is not going to move, which means that in the next cycle, the stage will be empty. So somehow you need to ensure that that stage is empty, right? How do you do that? Well, there are multiple ways of doing that. You can actually insert a no-op, or you can actually have a valid bit associated with the pipeline registers, right? And make the pipeline register invalid by setting that valid bit to 0. There are multiple ways of doing it. And both of them can actually work. So basically, in the end, what you have looks like this. You have valid bits associated with each pipeline register. It says, basically, the instruction, the contents of this pipeline register is valid or invalid. Invalid means it's basically a no-op, right? So if the instruction over here is stalling, it sets the valid bit to 0 at the end of the clock cycle. Now, a bubble basically propagates through the pipeline, right? That's one way of doing it. The other way of doing it is actually setting all the control signals such that the control signals correspond to a no-op, right? Such that that stage doesn't take any effect. Okay? That's why these are called bubbles or invalid instructions, no-ops. Okay. I guess I'll move quickly because you guys know all of this stuff, hopefully. Yeah? Okay, good, you don't. If you don't understand, let me know. Because you're going to implement this stuff. You need to ensure that those bubbles are inserted. You can do it in different ways, but these are the two fundamental ways. Okay, so stall conditions. Basically, this was a condition for stall, right? How do we actually implement this? You need to stall the instruction decode stage when instruction B, that's dependent, in ID stage wants to read a register to be written by instruction A in execute, memory, or write back stages. Right? Basically, you need to somehow detect this. And I'll give you the logic for this, which you will implement. It's pretty simple, right? It looks ugly, but it's really, what it's really doing is you need to generate a stall signal, a single stall signal in this decode stage. Let's take a look at the decode stage. So we have an instruction here. Oh, I want to look at both actually. And I've actually given you this logic earlier, right? If this instruction needs a source register, and if the source register of the instruction in the decode stage is the same as the destination register of the instruction in the execute stage, and the instruction in the execute stage is writing to a destination register, then the stall signal is true. Or, basically, you do this check for all of the stages. Does that make sense? This is what I showed you earlier. I'll show you again. Basically, if you look at this stage, this is the execute stage, and this is the memory stage, and this is the write back stage. And I'll do this for one source. Basically, there's a destination register in the execute stage. Maybe I should use the same terminology. Yeah, dest. I'll do it dr. dr execute. You basically compare the ID of this with the source register 1, let's say. If they're equal, and we need SR1 in this stage, I guess I called over here use RS, right? Use RS means if you actually need this register for this instruction over here, because some instructions may not need that register, right? It's a control signal. And basically, the instruction in the execute stage is writing to the destination register, because it may not write. If these are true, well, this is the AND gate over here. That means that you need to stall. So eventually, I'll generate a stall signal with this huge OR gate. That looks like an OR, right? And this is your stall signal. Basically, you need to do this for the instruction in the memory stage also. Memory stage has a destination register mem. Is it writing to the destination register? And does this need a source register? And does this source register ID match the destination register ID that's written by the instruction in the memory stage? If all of those conditions are true, this OR also evaluates to 1. And you do this for the write back stage, and you do this for all of the source registers as needed. So eventually you have a big logic, that's the stall logic, that's not shown here in that pipeline. Does that make sense? It's pretty simple to implement. So this is the combinational way of doing it. It's not the scoreboard way of doing it. Right? Scoreboard way would be different, in fact simpler. You don't need all of this combinational logic, right? You just need to check a bit or 2 bits, because if you have 2 source registers. Okay, so you'll implement this actually. I'm giving you part of your lab now. So it's of course, so once you have the stall signal, well, what do you do with the stall signal? Basically, stall signal actually serves as the write enable for the PC program counter, right? Basically, I guess if you do an inverter over here, that can directly be your write enable. And also, you can use the stall signal to set the valid bit, right? If stall is 1, valid bit should be 0, which means that you need an inverter also. Make sense? That's how you insert a bubble, basically. Pretty simple. But of course, you need to ensure that the execute, memory, and write back stages continue to advance normally during these stall cycles. While you're stalling here, hopefully something else is moving. Otherwise, you'll have a pipeline deadlock, right? In fact, when people first designed pipelines, they analyzed these pipelines. They needed to ensure that the pipeline moved, because this was done, let's say, 50, 60 years ago, right? The first pipelines people designed were not necessarily correct. So you need to ensure that there was no deadlock in the pipeline. And in your designs, you will need to deal with that also. If you make a mistake, if, for example, one of the stages doesn't move, well, good luck ensuring that your program completes, right? Okay. So let's take a look at, so this is the implementation of stalling. We'll take a look at the implementation of data forwarding later. Let's take a look at the impact of stalling on performance first. Each stall cycle, whenever you're stalling, really, what you're inserting a bubble into the pipeline. What that means is you have one lost cycle, right? No instruction can be completed, because once you insert a bubble, one cycle, eventually an instruction will not be completed. So if you insert n stalls, you'll have n bubbles. Let's do the calculation. Remember the performance equation. Execution time is equal to number of instructions times cycle per instruction times clock cycle time. Stalls actually affect the cycles per instruction part, right? It doesn't affect the number of instructions. It does actually if you handle all of the stalls in software. That's a different thinking. It doesn't affect the clock cycle. Does it? Well, it may, right? If this logic is horribly complex. Well, can you guys see this? You should really shout if you're not seeing the screen. Because I'm seeing stuff here, but you may not be seeing it. Okay. It might if this logic is complex, right? So stall logic actually can affect all of those values. Number of clock cycles, number of instructions if you're handling stalls in software. Cycles per instruction, which you will analyze, and clock cycle time. If this is actually extending your clock cycle, which it might, think about a 30-stage deep pipeline like Intel Pentium Prescott. If you're actually doing this combinational dependence check across 25 stages, let's say, that's a huge logic, right? With a huge critical path, perhaps. Well, they didn't do it this way. They had out-of-order execution, which we will talk about. But it could affect your clock cycle time. Assume that it doesn't, and in a good design, it really shouldn't. Assume it just affects cycles per instruction. If you have n instructions and s stall cycles, then average cycles per instruction is n plus s divided by n. Make sense? This is perfect pipeline. Normally, you would have one instruction per cycle, assuming your s is 0. But because you're stalling, you'll have n plus s divided by n. Ideally, you would like to have s 0. So what does s depend on? It depends on the frequency of read after write dependencies. How often do these happen? If they never happen, that's great, right? Or if the read after write dependencies, if the distance of these dependencies are always greater than 4 in this case, or greater than or equal to 4, you will never have a problem. It depends on the exact distance between the dependent instructions. That's what I just mentioned. It depends on the distance between the dependencies also. Okay. For example, if I1 and I2 and I3 all depend on I0, once I1's dependence is resolved, I2 and I3 must be okay too, right? Because you're doing sequential execution. Okay. Does anyone know what this code does? That could be a good question on an exam, I guess. Anyway, you don't need to know right now. You can figure it out. It's actually interesting. Well, you need to know what's happening here, but it has some conditions over here. But anyway, this code translates to this assembly in MIPS. And if you look at this assembly, a lot of things are dependent on each other. For example, this add is writing to S1, and this shift left is actually reading from S1. If you actually follow all of these dependencies, you need to add 3 stall cycles among those. Why? Because assuming we're not doing data forwarding, the instruction that's over here needs to wait until its parent instruction writes to the register file. And this code is scheduled by the compiler such that the dependent instruction comes right after the instruction that's writing to the register that the dependent instruction needs. That's why you need to have 3 stalls. Somebody needs to insert those stalls. Assuming hardware does it, then you have this. If the software does it, then the software needs to add 3 no-ops, right? Okay? Of course, maybe there's a better way of scheduling this, but we'll not get into it right now. Maybe if you have a better software, a better compiler, maybe you would reorder the instructions such that you can minimize the stalls. That could be a good question, actually. Homework question, maybe. How would you actually reschedule this code such that you minimize the number of stalls? Think about it. Okay, this is pretty bad for this. But actually, we can eliminate most of these stalls by data forwarding. If we had the ability to forward data when the data value becomes available, I'll show you that we can eliminate actually almost all of these stalls. There will be 1 stall that's left. And that's going to be difficult to eliminate in this pipeline structure. So let's take a look at it. I've already introduced data forwarding, so the basic idea you know. It's also called data bypassing. It's basically forward the value of to the dependent instruction as soon as the value is available. Now I'll give you some, I guess, philosophical things over here, which is, this is really a data flow principle, right? When the data is available, supply it to the destination. Data value is supplied to the dependent instruction as soon as it's available, and the instruction executes when all of its operands are available, instead of waiting until something is written to the register file, right? So data forwarding actually brings a pipeline closer to the data flow execution principles. It's not completely data flow. We don't eliminate all of the, we're still sequential execution, right? We don't eliminate the program counter, if you remember the lecture 2. But you're really supplying the data as soon as it's available. And it makes sense to do this also, but it comes at additional complexity, as we will see. So this kind of, I'd like you to stretch your mind and think about the registers and memory as something different. Normally, you think of them as state, right? Register has some state. Memory has some state. It stores some state. It's intuitive to think of them that way. Basically, if you have add Rx, Ry, Rz, it means get values from Rf, register file location Ry, register file location Rz, and put the result in register file location Rx. But this is actually really a part of the communication abstraction. This storage over here is really enabling communication between instructions. You may not really need the storage location. It's really a name for a value that's being communicated. Right? We can think of the same instruction as get the results of the last instructions to define the values of register Y and register Z, respectively, until another instruction redefines register X. Younger instructions that refer to register X should use this instruction's result. Make sense? So registers actually are just names for values to be communicated between instructions. Which means that what matters is to maintain the correct flow of data or flow of values between instructions. And as long as the flow of values is correct between instructions, maybe you don't really care about what's happening in the register file, right? Register file may have some value that's not updated, maybe, but the instruction may get the correct value. And we will actually see this in out-of-order execution a lot. What really matters is to maintain the correct data flow, value communication between different operations. As a result, instead of waiting, so this is add that's writing to register Z, this is add that's reading from register Z. Instead of waiting for the first add to write its data value into the register file to move this add in the pipeline, what we can do is this. This add, as soon as it produces its value, which happens at the end of the execute stage, I keep forgetting this, which happens at the end of the execute stage, supply it with some other path to this add, such that this add can move on and execute, and write to the register only after write back stage is done. Which means that during this time, register file doesn't have the value that this instruction captured, right? This instruction captured the latest definition of register Z through this forwarding path. But register file doesn't matter because it's really something that stores the value, something that needs to be updated at some point, right? As long as you communicate the values correctly between instructions, you can execute correctly. And we will see that in out-of-order execution also. Out-of-order execution will happen that way. Basically, register file needs to be correct only when it's exposed to the programmer. Underneath, as long as the instructions get their values correctly and execute correctly, no problem. Register file can be out of date. Only when the programmer needs to examine the register file that it needs to be correct, right? We'll see that. And when does the programmer examine? Basically, the programmer needs to actually look at the register file state at the end of the write back cycle. Okay. Okay, so you got the idea. So how do you actually do this forwarding? Remember, this is actually the same if you haven't realized that. This is basically the definition of dependence. Basically, if instruction B in ID stage reads a register written by an instruction A in execute, memory, or write back stages, then the operand required by IB is not yet in RF. It is not yet in the register file. But we can retrieve the operand from the data path instead of the register file. And we can retrieve, well, we have to retrieve the operand from the youngest definition of the register, if there are multiple definitions outstanding. Well, what does this mean? Okay, I have both of them over here. I guess I'll show on this one. So if you have an instruction that needs the value that's written by any of these instructions over here, what we can do is we can provide paths called forwarding paths to the instruction that's waiting here. So let's take a look at one example. Let's assume that the instruction add is producing a value, and this instruction actually needs that value. Well, this is the forwarding path that takes ALU's result and puts it over here. And it also actually puts it over here. So now this instruction, this particular instruction that's waiting here, can get its value from the register file if it's available, or this location, which is the result of the ALU, or this place, which is the result of data memory or the instruction that actually generated the result from the ALU, or this place, right? So instead of reading from the register file, you can actually capture values from the execute stage, memory stage, and write back stage. These are the 3 different forwarding paths over here. I'll show it again. Make sense? Well, you could actually implement this last one as internal forwarding also. If your register file is such that, for example, this instruction over here that's writing to the register file, basically you can have part of this mux inside the register file. You can think about what that means. It's pretty simple. Make sense? So what does this require? This requires certainly additional forwarding paths that didn't exist before. Remember the old pipeline? We didn't have this forwarding path. There was no need to communicate a value from a later stage to a previous stage. We always wrote back to the register file. This was the only path that we had actually. If you follow this write back path, you always wrote to the register file. Now we need to add these forwarding paths, new buses, and we need to add these muxes, right? Now a source register or source operand, let me not call it a register necessarily because it's a value that's to be communicated. Source operand can come from the register file, the ALU stage, execute stage, the memory stage, or the write back stage. So now you have a wide mux over here. And somehow the forwarding unit needs to determine which value it should choose. And there's additional control logic over here. Does that make sense? Simple. So this is one way of designing the data path for forwarding. Remember, I put these muxes after the register file over here. Right? But there could be another way. That's the version 2. So they're before this pipeline register here. This is the decode stage, or decode and register file access stage, and this is the pipeline register. So you get the values, forwarded values, and you latch them here. This is the other way. You basically put the muxes after the pipeline register. Why would you want to do that? Or which one would you choose? I guess your answer is it depends. Depends on the critical path, right? For example, it may make sense to do this if you have enough enough slack, if you will, in the cycle time, such that adding these muxes doesn't increase your critical path. Whereas, but if your register file access takes very long, such that adding these muxes actually increase your critical path significantly, maybe that's not a good idea. Maybe this is a better idea then. Because now you're not adding muxes to this stage, you're really adding muxes to this stage, right? Okay, so that's a trade-off. I'm going to assume this second one over here because it looks nicer. But there's a trade-off that's being made here also. So the second one is actually, again, simple, basically. You do the muxing right before you can access the ALU. And it's the same thing. You can get the value from the register. You can get the value from the output of the ALU. But of course, now the output of the ALU needs to come from the next stage, right? You don't want to have a forwarding path directly connecting this, right? That makes no sense. Yeah. Because that would be using the result that you are supposed to produce in this cycle. Remember, this is a single instruction over here. So this is how you can forward the result of the ALU. This is how you can forward the result of the write-back register, the write-back stage. And there's one more actually we'll assume internal forwarding in the register file. Basically, if an instruction needs the value that's coming from the write-back stage, that's the forwarding path. We'll assume that it's happening in the register file. You can do this through muxes. You can do this through intelligent register file design. What does that mean? In the beginning of the clock cycle, you ensure that you can write to any register, and the second half of the clock cycle, you can read that value. Right? If you have a long enough cycle time or you have a good register file design, you can do that. Okay. Make sense? Any questions? You'll implement this also. Okay, what's the logic? Well, I assume that there's some magic that's happening here. But the logic over there is now simple also. It's basically very similar to the data depends logic, except it's maybe simple. You can read all of this, right? Basically, if you're in the execute stage, if your source register, if you have a source register, and if your source register is equal to the destination register of the instruction in the memory stage, and if the instruction in the memory stage is writing to a destination register, then use the forwarding path that's coming from the memory stage. That's how you determine the input of this muxes. Basically, this is the path you need to select, assuming all those conditions are true for this value. Otherwise, if that's not true, then you go to the next thing. And this needs to be ordered, right? If you're sourcing a register and the source register ID is the same as the destination register ID of the instruction in the write back stage, and if the instruction in the write back stage is writing a register, then forward the operand from the write back stage, basically from here. That's this path over here. And the last one, otherwise use the operand from the register file, because we're assuming the internal forwarding path. Make sense? So ordering definitely matters, right? Because there may be multiple instructions writing to the same register. You want to get the latest definition, if you will. What does latest definition mean? Latest definition is the value produced by the last instruction that writes to that register. So this is the youngest instruction. You need to select the youngest instruction. That's why this ordering is if, else, Well, why doesn't use RS appear in the forwarding logic? Because actually, if you're not using a value in the register, you're not you're not going to actually get the value over here. You can actually think about this. There are many ways of implementing this, so if you don't understand this, don't worry. But use RS means you actually need that value. Maybe you don't need that value, but this forwarding path determines how the data flows. Eventually, you're not going to latch the value anyway, right? So you can still have this implementation in the forwarding unit. I'll ask this though. So this doesn't take into account memory dependencies, right? And I'll let you think about them. Memory dependencies don't cause a problem in this simple pipeline over here, unfortunately. But in real pipelines, they do cause a problem, because real pipelines are much deeper than what's here. And we'll talk about that later. Okay, so let's take a look at what this can buy us. Let's do the same dependence analysis, except we're not talking about register write and register read anymore. We're talking about when is a value used and when is a value produced. If you look at R or I type instructions, they use a value in the execute stage. You need the value at the beginning of the execute stage, and they produce the value at the end of the execute stage, right? A load instruction uses a value at the beginning of the execute stage and produces its value at the end of the memory stage, right? And you can do the same analysis over here. These instructions don't actually produce values. So you can do the exact same dependence analysis that we've done before to ensure that the pipeline is actually moving safely, right? And if you do that analysis, you will see that if you have a load instruction that's producing a value at the mem stage and a dependent instruction that's using a value in the execute stage, there's no forwarding path that you can add to the pipeline to ensure that that value gets to the instruction that needs it in the execute stage. Well, why? I guess let's switch to this. I guess I'll switch to a nicer version of this also. So the load instruction is producing its value over here, right? And let's say this is a load. I guess load word into R1. And this is an add that needs R1. So it's a read after write dependence. In this cycle, when the load is accessing memory, add is already in this stage, right? Assuming you move the pipeline. So you need this value to actually do the addition. But if the add is already in this stage, it's too late, right? Just doesn't work because you actually increase your clock cycle to make it work. So if this is the case, if you have an instruction that's following the load, that's dependent on the load, you cannot move it over here. You need to stall this add before it moves to this stage. Does that make sense to everyone? Because it's too late. So if you look at this picture over here, before we had stalls between the dependent instructions, and we added 3 stalls. This was without forwarding, because every instruction needed to write back to the register file for the instruction that's dependent on to source the register. With forwarding, you can eliminate all of those stalls except for this stall. Basically, this shift instruction is dependent on this load instruction. The shift instruction needs to wait 1 cycle so that the load value is available by the time the shift instruction can start, before the shift instruction can start executing. Right? Is this clear to everyone? This is important. Basically, this shift instruction, well, I showed add over here. Let's say add. This add instruction needs to wait here. Load word is here. Basically, load word moves here, and then you insert a no-op here, such that the add gets the correct value. Because when the load word produces its result, now the add can continue. Okay? And this is exactly the reason why actually MIPS had a load delay slot. Because you cannot actually eliminate this, assuming you have a pipeline that looks like this. You cannot eliminate the stall with any kind of forwarding. So if you have a load delay slot, basically you always execute the instruction that comes after the load. If it's a no-op, that's good. If it's an independent instruction, that's even better. That way you can make progress. Well, we'll see that it's a bad idea. Right? What if you couldn't forward, or what if the distance needed to be 5 between the load and its dependent instruction, so that the dependent instruction could move forward? Do you need to have a delay slot for 5 instructions? Do you need to change the semantics of the load instruction such that all 5 instructions that come after the load instruction are always executed? Bad idea. We'll see this more in the branch delay slot. Okay. Any questions? Is this all clear? So you can all implement this without any bugs. No? You said all clear, which means that you should be able to. Okay, good. Well, debugging is a good way of learning, actually. It's perhaps the best way of learning, making mistakes and fixing them. Okay, I'll very briefly go through pipelining the LC3B. This is one of your handouts, actually. It's not necessarily required, but it can be instructive. This is not going to be your lab, but this was a lab in a past course I designed. It's a past lab I designed, actually. But it's kind of nice, because it kind of gives you, we've seen the LC3B microprogram data path. Now this talks about how you can actually pipeline that microprogram data path. I'm not going to go through this in detail, actually. It's a 5-stage pipeline. These are the stages. It's very, very similar to the MIPS pipeline that we've discussed. It's very conservative. Basically, you stall on branch and you stall on flow dependence. And this was, remember, the microprogram data path. And this is the pipeline data path. So if you look at this pipeline data path, it's very similar to what we've seen with MIPS. You have this PC mux over here. These are the valid bits to implement stalling. These are the control signals. And this is the control stall ROM. And this is the dependency check logic. Basically, you get everything that we've discussed happens over here. And this is conservative. There's no forwarding in this data path. This is the fetch stage. You can actually look at all of the control signals in that handout if you're interested. This is the decode stage. So remember the dependency check logic. Basically, it gets as input all of the register IDs from later stages. Address generation, memory, and also store result. This is the write back stage. and compares those register IDs with the register IDs that are coming from this stage, and the valid bits also. No, we forgot the valid bits, right? So you need to think about the valid bits also in your implementation. Right? If a later instruction is not valid, if this valid bit in the pipeline is not set, you'd better not forward that value. Because that instruction is a no-op, right? You've already injected a bubble into the pipeline. So you really need to gate. Basically, whenever you're doing something important, you need to gate the signals with the valid bits. Because valid says this instruction is actually valid. If this instruction is not valid, that instruction should not really affect the state at all, right? Which means that you also should not forward the data values from that instruction, because it's not an instruction really. Okay, I'm not going to go through this in detail, but this actually breaks down the microprogrammed LC3B data path into a pipeline data path. And if we had one more lab in this lecture, maybe in this class, maybe we could have done something like this. But you're already implementing this in MIPS anyway. Okay. And these are the control signals. So if you look at this, actually, the control signals are very similar to the control signals that you have in the microprogram machine. I mean, we discussed this, right? In the single cycle machine, you have some control signals. In the pipeline machine, you have some other control signals. They're really the same, except you may need some more control signals in the pipeline machine to set the valid bits, for example. And this is the control store for the pipeline machine. And these are some of the stall signals. Should I go through this? I guess I will go through this because this is interesting. So far, I've talked about stalling only in the decode stage, right? But there's no reason why this has to be done only in the decode stage. You stall when the value is not available. And you need that value, and you cannot forward that value, right? If you look at our previous pipeline, this instruction memory. Well, what if it takes 2 cycles to access? You need to stall for 1 cycle, right? Which means that you can generate a stall signal over here. That's kind of a weird stall signal, because stall signal means now you insert a bubble every other cycle, right? What if this instruction memory takes a variable number of cycles to access? Well, until you get the value, until you get the instruction, you'd better inject bubbles into the pipeline, right? So the value is not available. The value that you need, the data that you need is not available. If the registers that you need are not available, and if you cannot forward them, you need to stall here. What about here? This data memory. What if it takes a variable number of cycles to access? Again, the same thing. You stall the stage until you get the value from this data memory. And you inject a bubble into the later stages. So stall signals can be generated anywhere in the pipeline if the data value is not available. If you cannot move, basically. For some reason, if you cannot move, you have to stall. And there could be many, many reasons why you cannot move. Okay? Okay. And you can read the LC3B handout to see what stall signals there are. I'm not going to go through all of them. And this handout is over there. Okay. Maybe I'll ask you the questions, and then we'll take a quick break. And then we'll go into more dependence handling. It's a good question, right? Remember, this course is all about hardware versus software. It's not only about hardware. What is the role of hardware versus the software in dependence handling? We've kind of talked about this already. Software-based interlocking versus hardware-based interlocking. Should you do only one? Should you do both? Well, both may be a good idea, actually. But maybe the software does its best to schedule instructions and leaves the rest to the hardware, right? That's probably a good idea. And we'll talk about static instruction scheduling later on. It's probably very difficult to do just software-based interlocking, right? Unless you have a very specialized application domain where you can schedule the instructions really, really well. Who inserts or manages the pipeline bubbles? Basically, if you do software-based interlocking, software actually manages the pipeline bubbles. Who finds the independent instructions to fill empty pipeline slots? Once you insert, basically, if you don't want bubbles in the pipeline, maybe you want to reschedule the instructions such that you don't have any bubbles, right? Such that instead of such that you add independent instructions between the dependent instructions such that the pipeline never stalls. That's the idea of static instruction scheduling. But the hardware can do this also. That's out-of-order execution. And we will see that how the hardware does it. It comes at the cost of additional complexity. Think about the advantages and disadvantages of each. And we will cover both software-based instruction scheduling and hardware-based. So this leads to the other question. What is the role of the hardware versus software in the order in which instructions are executed in the pipeline? Basically, it's kind of the same question restated, right? You're handling data dependency either in software or hardware, which means that you're really changing the order of instructions that are handled in the pipeline. So if you change the order in software, this is called static scheduling. Basically, software changes the order, compiler changes the order, or the programmer changes the order such that the pipeline is moving nicely. There are no stalls, if it's possible. That's the ideal. Or you can have hardware do this. In fact, stalling in hardware is kind of scheduling the instructions, right? You're just waiting until you schedule the instruction in the pipeline. It's a very primitive form of dynamic scheduling, really. Well, in a sense, you're obeying the schedule that software provides you in the pipeline, but you're waiting for a while. But we'll see more aggressive forms of dynamic scheduling where the hardware reorders the instructions. Hardware says, oh, I cannot move this instruction because this instruction is really waiting. That's not what I wanted. I cannot move this add over here because it needs the value that's being produced by some other thing over here, and it's not available yet. But there are some later instructions that I've already fetched. Assume that this pipeline is longer now. There are some other instructions that I've already fetched that are independent. They don't need any values that are being produced in the pipeline. So why don't I send this down the pipeline? Or maybe down some other pipeline. That's the idea of dynamic instruction scheduling, which we will see. That's out-of-order execution. Okay, so hopefully you're stretching your minds a little bit now. There are many, many ways of designing an architecture. But let's think about the software-based scheduling a little bit before we take a break. What does that require? So compiler orders the instructions in this case, right? And hardware executes them in that order. In the dynamic scheduling case, hardware actually can execute the instructions out of the compiler's specified order. And we'll figure out how to do that later. How does the compiler know the latency of each instruction? For the compiler to be able to do this, schedule instructions in an intelligent way, it needs to know the latency of each instruction, right? How does it know that? Well, somebody needs to tell it that, right? How long does an add take? Yes? Exactly. It needs to be exposed somewhere, right? Especially if if the correctness of the program is dependent on this. Right? Somebody needs to expose these latencies to the compiler. Okay, let's assume that we actually expose these latencies to the compiler. We'll talk about, for example, VLIW architectures later, very long instruction word. The idea over there was to keep the hardware as simple as possible again, and let the compiler figure out all of the independent instructions and schedule instructions. So you need to expose the latency of each instruction to the compiler. And what happens if 5 years later you decide to design another processor and latencies change? Well, can the old code execute? This is why it's very difficult to just do software-based scheduling of instructions. Usually you really need some kind of hardware-based interlocking at least to detect dependence. It's very difficult to get away without the hardware-based interlocking, especially if you want to keep the same software, run it on a different kind of hardware, right? Redesign microarchitecture. Okay. That's a good exam question, actually. There are 3 pieces of information that compiler doesn't know that makes compiler's life really hard. Assume that it knows all the latencies, and it wants to schedule the instruction such that it minimizes pipeline stalls. Now, what does this take? Think about it a little bit. If the compiler needs to schedule instructions, it needs to move the instructions, right? It needs to find the independent instructions and somehow move them between dependent instructions such that you have enough distance between dependent instructions. But there are three pieces of information that makes this actually very difficult. Anybody guess? Three things, yes.
Can you lose efficiency based on the threading of the overall system? Like if there's internal threading going on, you can lose efficiency. It won't hurt your correctness.
So internal threading, I'm assuming this is all within a single thread, basically. Yeah, think about just a single thread. We're trying to schedule instructions within a single thread. Across threads, now let's not get into that. Assume that the threads are provided by the programmer and compiler doesn't mess with that. Yes?
The pipeline depth may be the microarchitecture level, not the ISA level.
That's right. I mean, that's true, but I'm assuming that that's already exposed to the compiler. I'll give you that. Because otherwise it's very difficult for the compiler to really understand where to schedule things. Cache misses, there you go. There's one. Basically, more generally, the latency of an instruction, actually. Some latencies, I said, well, I kind of lied to you. Compiler knows all the latencies. Well, yes, true, but maybe compiler knows the worst case and best case latencies. But it doesn't know if an instruction takes variable latency, right? If that latency is dependent on some dynamic condition. What is that? Well, the caches, for example. A load instruction. Compiler has no idea whether the load instruction actually hits or misses in the cache. We'll talk about caches later, but you've covered the basic idea of caches, right? If the load instruction hits in the cache, it takes 1 cycle. If it misses in the cache, well, it may take 10 cycles, 30 cycles, 50 cycles, 500 cycles, depending on which level it misses. Now, how does the compiler schedule the instructions? It doesn't know this. That's a challenge. That makes life very hard for the compiler. That's one example. What else? 2 more. Remember, and this makes basically exactly this makes it difficult to move instructions in the code because you don't know which instructions to move. You don't know how many instructions to move after a load. 2 more. Yes?
Maybe if there are control flow instructions.
That's right. Basically, that's true about a particular kind of control flow instruction, which is the direction of a branch, right? Where does the branch go? Again, the compiler doesn't know this, right? This happens, this is determined, unless if it's an unconditional branch, it's easy, right? You know that you're going to jump. But if it's a conditional branch, the compiler doesn't know that condition, which means that it has difficulty in moving instructions after a branch, right? Let's assume that you have some piece of code over here. It ends with a branch. And there are some dependent instructions over here. And you want to take an independent instruction from after the branch. Well, you don't even know where the branch is going. And compiler found an independent instruction here. Can it move it over here? Well, no. Well, I guess I'll be more civilized. I guess technologically advanced. That's the more appropriate word. But this is a branch instruction. You have some piece of code. Add. Let's do load and add over here. And this add is dependent on the load. And this branch instruction can go this way or this way. This is a control flow graph, if you will. We'll cover this a lot later on. Basically, this is a basic block. It's a piece of code with a single entry and single exit. Assume that you come here from some other basic block. You have this load instruction and you have this add instruction. Add instructions depend on the load instruction. And the branch, depending on the dynamic condition, can be taken, and this code can be executed, and can be not taken, and this code can be executed. And the compiler does dependent analysis and says, oh, there's a subtract instruction over here that's independent of anything over here. And I can actually move the subtract instruction in between load and add so that the add doesn't need to wait for the load. I can eliminate a bubble, right? Eliminate a stall. That's probably a good idea, But now the compiler doesn't know if the branch will be taken or not taken, right? This works if the branch is not taken. What if dynamically branch is taken and compiler actually moved the subtract over here? Well, you've modified some state that will affect this part, right? So that makes it difficult for the compiler. The existence of this branch, the sole existence of this branch over here, makes it difficult for the compiler to actually move instructions freely. If this was straight line code, no problem, right? Basically load word, add, no branches at all, and there's a subtract here. And the subtract is actually independent of everything that comes before it. Compiler can do this movement, and it's not a problem because all of this code will be executed, all of the dependencies are satisfied because you know that the subtract is actually independent of everything before it. Here, a difficult issue, right? Because there's something over here that may be dependent on the subtract. It's harder for the compiler to do. And we'll actually see methods of actually doing this or trying to do this as much well at the compiler level. What else? There's one more thing. Yes?
If there's like things that might happen that's hard to predict statically, such as hardware exceptions, like machine checks, stuff like that.
So that's a good question. That's why I don't want to add it over here, but
Really?
that affects compiler's ability to move stuff also, but I don't want to put that over here.
We might
You're right.
jump to another function. In the
That's
middle
right,
of
yes.
execution, right?
So that's something that the compiler always needs to handle when it does code movement, actually. It needs to ensure the correctness. It needs to ensure that the exceptions are handled at the right place. How many of you have actually debugged optimized code? Have you actually, let's say you wrote a program, you ran it through GCC -04. Do you know what I'm talking about?
Yes.
Yeah, basically it optimizes the code. It's very difficult to debug, right? Because the compiler reorders instructions. As a result, things may happen that's unexpected. So it kind of changes the ordering of the instructions, even though it doesn't change the semantics of the program in the end. Hopefully it doesn't change the semantics of the result. It may also. Devising correct compiler is an important thing too. But basically, yes, you're right, absolutely right. The compiler needs to ensure that that happens. And that does get in the way of scheduling, but that's something that is required to do for correctness. And we'll talk about that. One more thing. I'll give it to you, okay. Well, I guess there's here. This is the real answer. Anything that's determined at runtime. And what's determined at the runtime? Variable length operation latency. We talked about cache misses. That's one example. Actually, that's not only limited to cache misses. It could be limited to arithmetic units also. Let's say you're doing multiply. And you've designed a multiplier such that it takes one cycle if one of the inputs is 0. That's determined at runtime, right? Because the value of the inputs is determined at runtime. If it's 0, it takes one cycle. If it's not 0, it takes 8 cycles. Okay, that's one example. Branch direction we've talked about. You don't know the branch direction, so it's difficult to figure out how to move. By the way, let me say something over here. The compiler actually can do this movement, put the subtract over here. But what happens is it needs to ensure correctness on this path also. If the branch is actually taken, it basically does an add. It needs to compensate for the subtract. This is called compensation code or fix-up code. If you move the subtract over here, you need to ensure that if you take this path works correctly, so you then add to undo the effects of the subtract. Does that make sense? That's called fix-up code. Actually, and even better, so this is one example. There are many ways of actually things happening in code. Let's say you have the same subtract over here. R2, R3, subtract R1, R2, R3. Now the compiler can move the subtract because subtract happens in both cases. That's great. That's the best case, if you will. Right. Okay, anyway, let's not go into the code scheduling lecture today. The last thing is really memory addresses. So memory addresses are also not known to the compiler. The compiler knows the register addresses, so it can do the dependency analysis on the registers very well. It can say this instruction is dependent on this instruction just by looking at the registers. But what about memory? Well, that's difficult. Especially if you have pointers, it's very difficult. So let's take a look at a similar piece of code. Load, store, load. And there's some address computation that's happening here. There's some address computation that's happening here. Address computation that's happening here. Can you move this load over the store? The compiler may not be able to figure this out, right? Because the addresses of store and load are determined dynamically. Let's assume that this address is determined by using R4 as a base register. This address is determined by using R5 as a base register. If the compiler cannot know what the values are in R4 and then R5, it cannot do this movement safely. It has to be conservative. It has to assume that this store and load are dependent. That's the third information, memory address. It's really determined dynamically during execution, depending on the addressing mode, of course, right? Okay. I'll ask you one question, and I promise I'll take a break after this. What can the compiler do to alleviate this, actually? It has a lot of these unknowns. Can it somehow estimate these unknowns?
You can run general test cases and see how much time it takes.
Okay, that's good. Basically, that's the idea of profiling. What it can do is it can run the program with some representative inputs, if you will, and profile the code and say, okay, this load instruction, or let's go back to the code example that I gave you earlier. This mess over here. Compiler runs the code with many, many inputs that the programmer specifies and figures out this branch at this location is always not taken. And it says, oh, most of the time I profile this code, actually all of the time I profile this code, this branch is never taken. So I'm going to actually assume that this branch is not taken, move the subtract over here, and add this fix-up code. That way, most of the time, instructions actually go this way, hopefully, if your input set is representative. When you actually run the program, you actually go this way. As a result, your scheduling is good. Right? The compiler did the right thing in that case. So that's how the compiler can potentially overcome this. Not perfectly, of course, right? What if the profile is not accurate? You run these test cases and you run these test inputs. This is called input data set, by the way. Basically, you have some input set into the program. And you can profile the program with representative input sets, hopefully representative. If they're indicative of what you're going to run in real life, then you can do the scheduling nicely, perhaps. But what if the real execution has some taken paths? In fact, in real execution, this branch may be mostly taken, right? In that case, you schedule the code such that you execute the sub over here, and you execute add over here. Now you've added two useless instructions that you always execute. Now your performance goes down, right? Does that make sense? So you're trying to fix stalls, but you're really adding stalls, depending on where the branch goes. So profiling is a very effective technique, and we will see this actually when we talk about control dependence handling. Assuming the input set is representative, assuming the information you get is correct. It applies to loads also, right? The compiler can run the program and says, this load always sits in the cache. So I'm going to assume it will hit in the cache, and I'm going to schedule the instructions such that the latency of the load is a cache hit latency. Yes, you had a question?
Oh, is it possible to compile at runtime, such as a JIT compiler?
That's a great question, yeah. People have tried to overcome a lot of these downsides. And if you have a dynamic compiler, a just-in-time compiler, you can still you can actually try to learn this dynamically. You're absolutely right. The downside is, if you look at, you can think of this as a dynamic translation, right? We go back to what we've discussed earlier. Remember Transmeta, the code morphing software? That's exactly doing that, actually. It's doing this dynamic translation. It's not only translating one ISA to another ISA, it's also figuring out the hot paths. It's trying to schedule instructions such that you get good performance. And it's trying to learn the dynamic behavior of the branches. So if you have a dynamic compiler, you can perhaps learn much better. Instead of using a profile input set and relying on the profile input set, you can learn based on the execution that's happening. But you may not be able to adapt quickly. Because let's say you figured out this branch instruction goes taken all the time. You go into a mode where you dynamically recompile the code, and you switch to that mode, and maybe the branch instruction now switches back, depending on the input set, right? So there's overhead to dynamic compilation, but that's a very good way actually approximating learning the dynamic behavior. Yes?
Can you do good enough profiling for a general purpose computer?
Depends. It depends is the right answer, right? So for profiling to be good, first of all, your profile input set needs to be good. If that's not good, then all bets are off, right? You can do it in your if you can actually provide input sets to GCC and try how good it is. Okay, I'll give you some examples in branch handling. So let's take a break. This time I'll give you a 4-minute break because that rounds us off to 1900 Portugal time. And then we'll start control dependence handling. Dependence handling. But we've spent some good amount of time on what makes software-based instruction scheduling difficult. So hopefully you guys have some good ideas now. Let's review control dependence. Basically, the question is, what should be the PC we're going to fetch from in the next cycle? And the answer is the address of the next instruction, obviously. And all instructions are control dependent on the previous ones. And I've given you this earlier. So there are several interesting questions here, actually. If the instruction that is fetched is a control flow instruction, how do we determine the next fetch PC? In fact, how do we know the instruction is a control flow instruction, right? We haven't even decoded the instruction yet in the pipeline. The decode stage comes after the fetch stage. So let's take a look at some branch types to actually see how complicated the problem can get. There's actually not one kind of branch. You can classify branches based on their types: conditional, unconditional, call, return, indirect. And there may be other types depending on the ISA. Direction at fetch time, if it's known, that may be good, right? Unconditional branches, known. Calls, known. Returns, known. Indirects, they're known. These are always taken branches. Conditional branches are unknown. Number of possible next fetch addresses are also different depending on instructions. Conditional branches usually have 2 targets. Not many ISAs have conditional indirect branches. Conditional branches are usually dependent on the target is dependent on the register, and the fall-through address is PC plus instruction size. Unconditional branches and calls usually have 1 target, but you can have returns and indirect branches that have many, many targets because they're register dependent. And unconditional branches and calls, they could be dependent on the program counter. Remember, in the MIPS you have concatenation with the program counter. So different branch types can actually be handled differently. And we'll get back to this later on. For example, calls and returns have a particular behavior in most programs. You call, and then you return. It's kind of nested, right? You have a nested set of calls and then nested set of returns. So you can exploit that. If you think about that, you can actually use a stack to predict the return addresses, right? Because whenever you call, you're going to return back, hopefully, to the next instruction, right? And you can push the address of the next instruction on a stack. And whenever you see a call, you keep pushing. And whenever you see a return, you pop that off a stack. This is called a return address stack. And you can use that to predict the target address of the return. even though it may have many potential target addresses, you can actually use that stack to predict the return address by exploiting this property of nested calls in programs. Anyway, we'll get back to that. But there are many other types of branches, and you need to handle them correctly. Basically, we want to keep the pipeline full with the correct sequence of dynamic instructions whenever we have control dependence. And I'll give you 6 potential solutions here. There may be more. The first is, as with data dependencies, stall the pipeline until we know the next fetch address. And we'll see that this is a bad idea. Guess the next fetch address, branch prediction, or next fetch address prediction. We'll talk a lot about that in the next lecture. Employ delayed branching, branch delay slot. We'll talk about that. Do something else, applies here. Fine-grained multi-threading. I guess I could have asked you this. Basically, if you do fine-grained multi-threading, every cycle you switch to some other thread, the problem goes away, right? It's beautiful, as long as you have many threads. Eliminate these instructions. Well, if they're causing problems to you, so eliminate them, right? You could actually do that with control dependence, at least most control dependencies. It's called predicated execution. It's very hard to do it with flow dependencies, right? Basically, eliminate them actually means convert them to some hopefully easier to handle problem, which is data dependence. We'll see that also. And another idea that people have been very creative, because this has been a very fundamental problem in processor design. Well, why don't you execute from both paths and pick the right one in the end, right? Basically, enlarge your pipeline to be able to do that. It's called multi-path execution. And there are different forms of it. If you just go down 2 paths, it's called dual path. Well, what if you see another branch on the other path? Well, execute both paths too, right? So this could become exponential in the end if you have a deep pipeline. But we'll see this. This is actually an interesting solution too. Let's start with the dumbest solution. Stall the pipeline. And let's see why it's dumb. Let's assume we have non-control flow instruction. Because remember, every instruction is control dependent on the previous instruction. Let's assume that we have either non-control flow instructions or unconditional branch instructions. These instructions, you know the target of the next PC after you decode them, right? Well, if you stall the pipeline until you know the next PC, you need to actually have a bubble every other cycle. Bad idea, right? Because unconditional branches, you can actually resolve the target address at the end of the decode stage. Assume that the first one is an unconditional branch. You don't know the PC. You don't know where to fetch from in the next cycle, so you have a bubble over here. But you know the target address at the end of the decode for this instruction, so you can supply it to the instruction fetch stage at the end of the second cycle. But this means that you've lost you lost one cycle over here because you didn't fetch any instruction. So if you strictly stall fetch until next PC is available, you really get this kind of behavior. Because if you didn't stall fetch, actually, if you implicitly predicted that the next instruction is the next sequential instruction, you need to do something else. If that's a wrong prediction, you need to squash that instruction, right? So we'll see the idea of squashing also. So this is a bad idea. Oh, that didn't work. Okay. Okay, so you can do better than this, certainly. Rather than waiting for true dependence on the PC to resolve, just guess next PC equals PC plus 4 to keep fetching every cycle. This is the simplest form of prediction, right? Always predict you're going to the next instruction. Probably a good idea. Is this a good idea? Yeah? Actually, this is a good idea. But it has its downsides. So what is the upside of stalling fetch until next PC is available?
You don't have to fix any wrong.
Exactly. You're never wrong. Very conservative, but never wrong. If you're wrong, basically you don't need to fix. Whereas here, you need to fix if you're wrong, right? Fixing means somehow invalidate the stuff that you fetched, right? Okay. Let's see why this is a good idea. Let's assume that 20% of the instruction mix is control flow. 50% of forward control flow is taken. This is forward control flow means if then else. And backward control flow, think about a loop. Basically, backward control flow means the target address of the branch is smaller than the address of the branch itself. Forward control flow means the target address of the branch is larger than the address of the branch itself. And backward is usually loops. And usually loops are taken in programs. And in fact, people have done these studies. This is one particular paper. Typically in programs, they found out that most of the branches are taken. Around 70%, 60-70% of the branches are taken because a lot of the programs have loop branches. And again, this is a very, very average number. Your program may have 0% of the branches taken, right? Unlikely, but could happen. So if you're doing this prediction, next PC equals PC plus 4, you're actually correct 86% of the time. For 86 out of 100 instructions you fetch, you're correct. Why? Well, because 80 of the instructions are non-control flow instructions. So 80 of those instructions you're correct anyway. And out of the 20%, 30% of the 20% you're correct. Because 30% is not taken, right? So you get 80 plus 6, 86 out of 100 instructions. Not bad, right? 14% of the time you're incorrect. Okay, so we're still guessing. Basically, always predict the next sequential instructions, the next instruction to be executed. This is really a form of next fetch address prediction and branch prediction. Even though the instruction is not a branch, you're really predicting the next fetch address. How can you make this more effective? Now, I've given you some numbers. 30% not taken, 70% taken. And we want to still do a PC, next PC equals PC plus 4 because, well, I'm assuming that the instruction size is 4. Let's assume that. Because this is easy to do, right? You don't need to figure out the target address at all. You're always saying PC plus 4. How can you make this more effective? Any thoughts? How can you increase that from 86%, given what I've told you over here? No thoughts?
Assume the branch is always taken and
So you're proposing a different scheme. That's right. If you assume next PC equals the target, if you see a branch, first of all, you need to know a branch and you need to know the targets. I don't want that now. I want this prediction mechanism because it's really simple, but I want to make it more effective given this behavior of the programs. Well, you can try to maximize the chances that the next sequential instruction is the next instruction to be executed. Right? This works really well if basically the next instruction in sequence is the one that you really want to execute. How can you do this?
you can put the not taken part.
That's right, yes. Basically, remember profiling? We talked about this we didn't talk about it for no reason. If you somehow know what's the more likely path, you have a branch, and initially you have a taken path and not taken path, and you figured out this branch is mostly taken. Well, why doesn't the compiler lay out the code such that the taken path becomes not taken path? The compiler can lay out the code any way it likes, right? It can basically flip the taken path to be the not taken path, reorganize the layout of the code. Does that make sense? Basically, software lays out the control flow graph such that the likely next instruction is on the not taken path of a branch. This is a pretty cool idea, actually. It's called profile-guided code positioning. It was proposed by Pettis and Hansen in PLDI, Programming Language Design and Implementation, in 1990. And it works. Actually, a lot of compilers do this. Yes?
It sounds like it couldn't work with loops.
That's right.
Yeah.
It doesn't work in all cases, you're right. How do you do it with loops, right? Maybe difficult. But it works if you have something like this. You have a branch that looks like this. This is called a hammock branch also. It looks like a hammock. It's an if-then-else branch, basically. If some condition, do this, else do this, right? And I'm going to say this is block A, block B, block C, block D. This is taken, this is not taken. And if you label the blocks in the code, this is block A is here, block B is here because this is the taken path, block C is here, and block D is really here. That's what it looks like in the code. And let's say compiler profiles the code and looks at the frequencies at which these paths are exercised and says, 99.999% of the time, this branch is taken. Well, what it does is basically it lays out the code such that the code layout looks like this. If that's the case, you really want to do something like this perhaps. Actually, you don't really want to do something like this. You want to do something like this. Does that make sense? This is the layout of the code. Increasing addresses, sequential addresses. Because remember, if you have, there's an unconditional jump here. And there's an unconditional jump over here also. So basically, you have the branch here, and you don't even need to have a jump over here, basically, in that case. Okay. You don't, right? Because it's next sequential code. You're assuming this is the only transition. You're questioning, but
This thing backwards.
Yeah, it should be ABD.
wait.
It should be
Oh yeah, ABD. That's right. Thank you. I appreciate that. That's right. Basically, what we've done essentially, this should be ABD. Now you agree with the unconditional jump, right? Yes. Basically, this unconditional jump always goes through B, assuming this is the only path you can go from B through D. Basically, what we've done here is we've flipped the taken path to not taken, and the not taken path to taken. That's what the software did. If the software has this information, it can do this powerfully. Now, for this branch, next PC equals PC plus 4 is almost always correct, right? Very powerful. It's profile guided code positioning. And you can read that paper. It's a beautiful paper. So a lot of compilers actually can do this. Okay, let's say you don't have this in the compiler. Can the hardware do this? Now tougher, right? I don't know if you will get to it, but actually some of the hardware that you may have used does this. Intel Pentium 4, for example, has the idea of a trace cache. What it does is, as it executes the programs, I guess I should not switch so quickly, it records traces of basic blocks. Let's say the program is being executed on the hardware, and you always go ABD, ABD, ABD. In the first execution, and ABD has instructions, of course, right? Let's assume each of them have 5 instructions. 5 instructions, 5 instructions, 5 instructions. So you have 15 instructions. Pentium 4 takes those 15 instructions, puts them in a cache, such that you can get those 15 instructions in a sequential manner. Kind of a nice idea, right? That's the idea of a trace cache, actually. You're really storing the traces of executed instructions, such that instructions that are fetched in sequential order are actually placed sequentially in storage. Not in memory, but in a microarchitectural structure called trace cache, where you can fetch things in a sequential manner. Software is doing the same thing, profile guide code positioning, except it's storing things in sequential order in memory. If the software doesn't do that, the hardware can do it. And there are trade-offs associated with it, right? Obviously, you add more complexity into the hardware by doing this. But you can adapt to changes much more quickly. What if sometimes you do ABD? At the first half of the program goes through ABD. Second half, you go through ACD. Somehow data values are like that. Trace cache can adapt to it. Initially, it stores ABD, and it keeps being correct. Later, when the trace of execution changes to ACD, it scraps the ABD, it stores ACD, and it's correct after that. That's the advantage of the dynamic hardware approach, whereas the software has a single layout. Although you could try to fix that also, right? You could have ABD and ACD stored there, and you could have a branch to pick But now that branch needs to be predicted correctly. Okay? Yes?
Does the PC now fetch from the trace cache?
That's right, exactly. So if you look at Intel Pentium 4, the PC fetches from the trace cache, assuming there's a trace cache hit. So that's the complexity that needs to be added to the hardware to be able to do this.
But how will it know if it's wrong? I mean, it's wrong.
Well, you eventually execute the instructions here, right? There's a branch at the end of A that you execute. If the target is not C, of course you need to have enough metadata here saying the target needs to be C. Right? I haven't given you the full mechanism. But you need to have enough information over here to figure out whether you're wrong or correct. Okay, if you're interested, you can read the trace cache articles. Okay, how else can you make this more effective? Let's talk about this a little bit and then we'll stop. Well, I guess I'm giving you how else. Get rid of control flow instructions or minimize their occurrence, right? This is one other way. How do you do that? There are two ways of getting rid of control flow instructions. One is getting rid of unnecessary control flow instructions by combining predicates. This is called predicate combining. And I'll give you that idea. And the second is convert the control dependence to the data dependence. This is called predicated execution. And these are two different things. Let's look at predicate combining. If you look at this example, you have a branch that has three conditions, right? You execute this code inside the if statement only if all of these three conditions are evaluated true. There are two ways of implementing this. One is you can have three conditional branches, right? You can basically have a BEQ on A and B registers, and then BLT on C and D registers, and BGT on A and an immediate, if it's possible, or another register where you store 5,000. So basically, the compiler can generate code. Oh, I guess I'll reuse some of this. You have a BEQ. You have, did I say BGT? No, that's the BLT, and then BGT. And if all of them are, well, well, I guess you can do the negative of them, but only if, I'll do B not EQ, B not LT, B not GT, so that I'll make life easier for myself. Okay? So if not equal, you jump out of the if statement. And this is the if statement, let's say. If not greater than, you jump out. If not less than, you jump out. If not greater than, you jump out. So you need to execute three branches if this is the case. Well, this increases the number of control dependencies, right? Now you need to predict three of them. Predicate combining, the idea is combine the predicate operations to feed a single branch instruction instead of having one branch for each. Basically, instead of testing all of these conditions, you basically convert these into an outcome. Basically, you test, you have a compare A and B, and put the result into a register, and then compare, and compare can be equal, and then compare greater than, less than, compare greater than, and you can imagine the input values. This is the second condition, third condition. And actually what you can do is, some ISAs have condition registers. Let's say condition register 1, bit 0. Condition register 1, bit 1. Condition register 1, bit 2. Now you have the conditions in a single condition register, right? Maybe 3 bits over here. If all of them are true, then you jump. Basically branch, I'm just inventing instructions here. All condition bits set, condition register 1. Right? Actually, you can do it much more easily. If none of them is set, then you jump out, right? Okay, that's probably better. Branch condition register 0, condition register 1. Basically, you test the bits in the condition register, and you branch out if the condition register is 0. Well, anyway, you can imagine the logic over there. Basically, all need to be 1 so that you go in over here, right? So I guess not equal, not LT, not greater than is probably a better idea. Okay? So we go back to that. So now you can branch out of condition register 0. Does that make sense? Now you combine the predicates and you're really testing one thing, one value, with a single branch instead of having 3 branches over here. As a result, you've eliminated the instructions. I guess I've given you the idea over here. The upside of this, now you have fewer branches in code, fewer mispredictions and stalls, hopefully. The downside, you have possibly unnecessary work, right? Why? Because if the first predicate was false over here, you would jump out quickly without executing anything over here. Whereas right now, you need to execute this, execute this, execute this, execute this. Only after that you determine whether you jump out, even if the first predicate is false. So you're always executing potentially unnecessary code. That's actually a fundamental trade-off. This is predicate combining. You're really combining predicates. And as a result, eliminating some branches. A little bit different from predicate execution that I will briefly describe. But whenever you are getting rid of branches, you're actually increasing the amount of work you do. Yes? Good.
Is this always something you can do? Because it seems to me like a lot of the times when you're writing code, you're using short circuit evaluation to your advantage.
Uh-huh.
And it seems like this might you might be doing illegal operations at times, or like accessing illegal memory values.
Oh, I see what you mean. Yeah, I mean this is actually you're absolutely right. You need to ensure that the semantics of the program is correct. Yeah. So you may not be able to do that all the time. Okay. So these registers, actually condition registers, I didn't make them up. They exist in ISAs. For example, PowerPC has very powerful condition registers. You can manipulate all of these conditions and do the branching. Okay. I think I will stop here. Next time we'll start with predicate execution, converting control dependence to data dependence.